Hello, everyone. Today we are going to talk about nonlinear regression and residuals. In the last two lessons, we fit bivariant data, so two variable data with lines of best fit. Sometimes the linear model is not always the best choice. We can fit data with all sorts of curves. The most common are linear, exponential, and quadratic, but there are many other types. Before we look at exponential and quadratic, recall the general shape. So exponential are these two. This is growth, and this is decay. So if it's growing quickly, it's going to look like this one. If it's shrinking, it's going to look like the decay. And then our two parabolas. This has a negative A. This has a positive A. So exercise 1. Biologists are modeling the number of flu cases as it spreads particular city. The total number of cases Y is recorded on each day X after the total first reached 16. The data for the first week is shown below. Use your calculator to find the exponential regression equation for this data. So I want you to pause and I want you to put this data into list 1 and list 2. So you can see here on my calculator that I did stat edit list and I put my X values in list 1 and my Y values in list 2. So now I'm going to find the exponential regression. So to find that, I'm going to go to stat, calc, and you can see that if I arrow down, option 0 is exponential regression. So I hit enter. My X list is L1, my Y list is L2. If you did different lists, make sure you change those. And then my directions say to round to the nearest hundredth. So this is Y equals 15.92 times 1.12 to the X. Based on my regression equation, how many total weeks of flu will there be after 2 weeks? So after 2 weeks is 14 days. So I'm going to do Y equals 15.92 times 1.12 to the 14th power. So I'm going to exit out that, and I'm going to do 15.92 times 1.12 to the 14th power. And that is 77.8 if I round to the nearest tenth. So approximately 78 cases. According to your model, by what percent are the flu cases increasing? So to determine what percent, we have to remember our generic form of our exponential. So this is Y equals A times B to the X. So B is our growth rate. And if it's growing, at was always 1 plus the R. So since B equals 1.12, that's 1 plus our rate. So that means it's growing by 12%. Hospital officials will declare an emergency when the total number of cases exceeds 200. On what day will they need to declare this emergency? So the best way to do that is I'm going to go to Y equals, and I'm going to enter 15.92 times 1.12 to the X. And I want to know when it reaches 200. So I can look at this, and I entered something wrong there. I can look at my table to see when it's at 200. Or I could do a second graph of Y equals 200, change my window so that I get up that high. So see if I look at my graph, it's not over there far enough, so I'm going to change my window again. I'm going to make my maximum go up higher. So say 250. Oops, I only did 5. No. And now I can see where they cross. So now that I can see where they cross, I can do second calc, and I want to find the intersection of those two, which is 22 days. Actually, 23 days is when it will be over 200. If you don't like doing that system, I can have look at my table and look for where the blue is over 200, which again is at 23 days. Exercise 2. The cost per widget produced by a factory generally drops as more are produced, but then starts to rise again due to overtime cost and wear on the equipment. Quality control engineers recorded data on the cost of per widget component compared to the number of widgets produced. Why should a quadratic model be considered for this data set as opposed to a linear or exponential? So what I'm going to do is I'm going to pause, and I want you to put this into list 1 and list 2, and then come back. Okay, now that I've put my data in, while I was putting my data in, I noticed that my y values went down, and then they started to go up. So that's why it should be a parabola, because the y's go down, then up. Linear is always going up or always going down, and exponential is always going up or down, just at a much faster rate. So use my calculator to find the quadratic regression. So again, I put my list into list 1 and list 2. You go to stat, calc, and option 5 is quadratic. There's my list. And our equation, we're rounding to the nearest 10,000. So our equation is y equals 0.001 x squared minus 0.250 x plus 16.862 or 863. So we're going to do 3 and 4 tomorrow in class together. Now I want to talk about the correlation coefficient. In the last lesson, we saw how the correlation coefficient, or R value, measures the predictability of the model, or how well it will be to its predictions. Although the R value is an excellent measure, it does not tell us whether the model is appropriate, only whether it does a good job of predicting. Today we're going to talk about what is known as residuals and residual graphs. So the residual of a data point is defined by the difference between the observed y value and the predicted y value. We get our predicted from our equation. Generally, we do not want residuals to fall along the curve or make a pattern. If so, then it's likely that a linear model is not appropriate, and we should use exponential or quadratic. If the residuals are randomly distributed, then we say that the model is appropriate. So, exercise 1. Skydiver jumps from an airplane. Attached microchip records the time and speed for the diver for the 12 seconds of the diver's fall. The data is shown below. Find the equation of the line of best fit to the data and round everything to the 10th. As well, determine the correlation coefficient rounded to the 100th. And then decide if it's positive or negative. So I want you to pause and I want you to do part A. Okay, so I used my calculator and I found the equation. The linear regression is y equals 6.0x plus 13.1 with an R value of 0.94, which is a positive strong relation. So now for part B, I want to fill in the table with the predicted values, round to the nearest integer, and the residuals for each data point. So our predicted values are what we get from the equation. So if I put 0 in for x into my equation, I'm going to do 0 times 6 plus 13.1. So my predicted would be 13.1. I can do that for all of these manually, or I can go to y equals, and I'm going to enter my equation here. So it's 6.0x plus 13.1. Then I'm going to look at my table and remember that I need to use the x values I'm given. So at 0, it's 13.1. At 2, it's 25.1. At 4, it's 37.1. At 6, it's 49.1. 8, 61.1. 10 is 73.1. And 12. 85.1. Now for our residuals, what we're going to do is we are going to subtract actual minus predicted. Oops, I was supposed to round to the nearest integer. So I'm just going to get rid of all these 0.1s. So now our residual is our actual minus our predicted. So what we do is we do 0 minus 13, so that's negative 13. 25 minus 25 is 0. 46 minus 37 is 9. 60 minus 49 is 11. 68 minus 61 is 7. 72 minus 73 is negative 1. 74 minus 85 is negative 9. The residuals plot looks like that. Do you think this is good? And the answer is no. It falls in a pattern that very much looks like a parabola. So that means there is a better option, quadratic or exponential. So that's the end of our video. If you have any questions, please bring them to class.